vectors. We've already mentioned vectors before, or talked about them before. First day of lecture, maybe. A point that we refer to in geometry is nothing but a vector in space. The real number line is a one-dimensional space. The Cartesian plane is a two-dimensional space. 3D coordinate system, three-dimensional space. And so on, you'd have infinite dimensions. You may ask, well, why do we call it as a vector? Going back to, I say tomato, you say tomato. In physics, they would use direction. And the notation that they use in physics will be different than what I would use in practice in statistics. And what I use in statistics as a notation may not be the same in analysis. Only math make mistake analysis usually. But in terms of a practical application oriented notation, the two common ones are the directional ones and number two, the book introduces another notation. I will do that here. I will stick with that notation. That is a notation that you will see in mathematics, theoretical mathematics. In practice, we're just talking about matrices. So if you want to understand dimensions and put it to use in real life, you need matrices. Computers don't understand what the notation that we use, right? Okay, so what is the purpose of a vector? Why do we have the terminology vector to begin with? Well, if you take the number 2, do we agree that it is a number? Okay, that's what we call a scalar. A scalar has magnitude. The magnitude of the number 2 is 2. Good. In terms of a vector, this would become a 1D vector, a point on a coordinate. It's a 1D vector in a single dimensional space. If I write a point 2,4, we can't call that a scalar anymore because we are in 2 dimensions. When you have a point in 2 dimensions, naturally something else comes into play relative to the origin. I've touched up on this before, last time, the time before. What is that something else? Let's say where I'm standing is the origin. What's your name? Andrew. Andrew. Andrew's sitting over there. So in this representation, something else comes into play.
Direction.
Direction, right? Andrew is sitting at a certain angle, from me, right? So direction comes into play. So if I want to represent a point in a dimension that is not 1, I need to know direction. Same argument, if I stand here and look at that vent and say, well, I'm pointing at that vent, then it is at an angle. So naturally, direction becomes important. Jake, did you have something to say? Oh, same thing. Okay. Jake, correct. So if we're talking about higher dimensions, require magnitude and direction. So we've got to have a way to represent those two. What does a job for us? A vector does. Good. Let's take the matrix representation of that point. If I write it, I might either write it this way, or I can write it that way. Agreed. In practice, statistics, for example, when we mention or when we refer to vectors, we are referring to column vectors. Going to mathematics, the same concept. Math, we would use, oops, my bad. Well, I already read 2,4. That is fine, but oftentimes people confuse 2,4 as just a point. People don't recognize until they do a lot of practice. I can rewrite this way, 2,4. That tells me that we're talking about a vector. See the difference? So how I see it is no different from how a person who does pure mathematics sees it. Good, we're all talking about the same thing. Except physicists. Weird people. Here I thought I was weird. If we want to write that vector in physics, Jake, did they cover it yet?
Can you write in the matrix? You can write in the matrix.
Well, the basics of vector notation.
Use IJK.
IJK, right? We would write it as 2 times I vector plus 4 times J vector. That tells us direction. Direction along the x-axis. Direction along the y-axis. Put them together, you know exactly where that point is, right? How do we get to the point 2,4? Start at the origin. I go to 2, yes. Then I go up. That becomes 2,4.
Can you use I and J hat there instead of the vector symbol?
I hat and J hat, yeah.
Okay.
You can use I hat, J hat also. I didn't want to confuse.
My bad.
Because this is the most common notation that they would use in physics. Your book explains this, so I just want to stop here. You can use I had, J had also. So
Go ahead, sorry, I just wanted to clarify, so you can use that, the vector symbol, even though like it's unit 1. Like it's just
we
2,
will get that unit business later,
okay,
not here.
okay, sorry.
You can.
Okay.
Again, I don't want to confuse you all with multiple notations. What Chris is referring to, I can put a hat, except in statistics, we can't, then it would mean an estimator. Some would simply do IJK in boldface. And that would also indicate a vector. I think that's what Jake was referring to. There are multiple ways with which you can write a vector. I'm sticking to only the notation in the textbook so that you don't get confused. Good. It's just not in the textbook. I had to write it because I'm a statistician. Who's planning on taking linear algebra? So you will encounter this. With me so far? Good. We will encounter matrices in this class as well when the time comes. So the purpose of having a vector is to represent direction as well as magnitude. So I moved 2 steps along the x-axis, x direction. So this would become 2 I vector. Yes. Then I moved up y-axis 4 j vector. Yes. And relative to the origin from here to there, what is the next value relative to the origin? That would be 2i vector plus 4j vector. Yes, that's what your book will refer to as triangle law. Good. But this is all, this is what they're talking about. So if I represent the value 2, or if I make it arbitrary, call it sum A. I don't necessarily have to go in this direction along the x-axis always. Do you agree?
Yeah.
So I picked this so that you can understand the initial notation. I'm going to make it a bit arbitrary. And particularly, I'm going to do it in a way where I don't necessarily have to just move along the axis. Let's say I started at some point here. Good. Same picture. I moved in one direction. Then I turned, went in another direction. Yes. And I want to know relative to that point, where did I land? Same triangle law. So I can call it A vector, B vector, and that would become
C vector.
C vector. What does C vector equal to, Chris?
Us.
Caleb? That's your name, right?
Yeah.
Counter. Did you say something?
No, I didn't know.
Oh, no, he was right.
What's wait, Aiden? No, Kevin, huh?
Kevin,
Close. Kevin,
A plus B vector.
A vector plus B vector. Now, I could have omitted that, and that. I didn't initially because I simply wrote the number 2. Correct? If I didn't put 2 times I vector, then I wouldn't be referring it to a vector. I would think in my mind that it's just a scalar, a number. That is why this is twisted logic, you know. Physics people weird. That's more convenient in my opinion. But this serves a nice purpose also, particularly in physics, direction, magnitude matters. Do we understand? If this is confusing, when I said I'm talking about the exact same thing, what did I mean? Thoughts?
Could you say that again?
I mentioned earlier when I drew this, I'm doing the exact same thing. If you're not able to see it, well, let me rephrase that question. If you are able to see it, what did I just do? I'm referring to the fact that both are pretty much the same in terms of interpretation, but how?
The vectors are the same, like they're going the same direction,
Okay,
it's just tilted.
getting there, Rachel, correct? You're getting there, almost there.
A is a vector like I is a vector and B is a vector like J is a vector.
Okay,
You're just adding them together. Just because it's not the X or Y axis, it's
just
works
because
itself.
it's not the X and Y axis, but I wrote it as X and Y axis in terms of representation. And I'm referring both of them as triangle law. So Jake, did you have something to say?
I was wondering if you meant by the notation, like why the notation is different? or-
Not the notation, but interpretation. So Rachel used the word tilted, Chase used or explained just because you didn't use the X and the Y axis.
You just have like a shifted origin, doesn't really change.
You are getting close to Chris.
I was gonna say that I and J vector both move along 1 dimension, but A, B, and C both move along 2 dimensions.
No, it's still moving in 2 dimensions.
I is only along, if I is only along X, how,
I had an idea, but I was
What is that idea?
trying to remember.
Are you just
Maybe.
referring specifically to the resultants and how they get to the nearest point as soon as possible?
Well, perhaps you are not following my question properly. So here I wrote 2I, 4J. Yes,
Yes.
and I referred to as triangle law. Happy. Good. And I came here and I said, doesn't matter how you start, I can extend the logic and do it this way. Comfortable with this? I can rewrite it as AI vector plus B J vector. Oops, not there. But here, C J C vector. It's the resultant. AI vector plus B J vector. I can do it. But I sort of tilted using the same X and Y. Geometrically, the interpretation is the same. If you visualize what I'm trying to, I guess you're not able
The
to.
space between them is, I wanna say, no, not equidistant, but like the space between them doesn't change.
Okay, how about this? Go ahead, Chris.
are you trying to say that if you can write two different vectors that say the same thing in terms of where they're going, but they don't show the starting position.
Exactly. So instead of having it this way, I could do this. I'm sort of referring to the same thing. In purple, I can reorient the axis. Yes, I tilted the XY plane. I shifted its position, but I'm talking about the exact same thing. Yes, so concept being, you can take a vector, move it in a different point of starting point and refer to the same vector again. Good. If you complete this, in the sense, instead of going this way, then that way, I'm going to say there is another way to get to the exact same thing. Hey,
The resultant.
yeah, to get the results, and what is another way? So I went this way, in this direction, that direction, got a resultant. There is another way of doing it.
You talking about angles, like just like I'm
No.
confused now.
In terms of, walking and getting to, I walked over here, I walked over there, and got the resultant vector. There is another way to get to that point from the origin.
Straight line. I mean, just
Changing the order,
How, Jake?
like going up and then sideways.
That's it, right? Instead of going this way, that way, I could do, go up first. Right? Then turn it. Agreed. Looks silly. It's not. So, B vector, A vector, because the length is exactly the same, the resultant will be exactly the same. Agreed. Now, this completed version is what we call a parallelogram of vectors. So I'm going to move from here to there with me. Do you follow? And we're talking about the exact same thing. So I'm going to take that picture. In your mind, just visualize the two axes. That you've tilted the X and Y this way. If dancing is difficult for you in public, just imagine a bunch of vectors and keep going. Be good at dancing then. And try it next time you're in a club or a wedding. I don't think it'll serve you well, but you can try it. So I'm going to go with the next one. So I started here, went in that direction, turned in that direction, completed the resultant, yes? So A vector, B vector, A vector, plus B vector. I dropped the I in J. Any reason as to why? I'm building it up for a reason. Haley, go ahead.
You're changing the axis.
I'm changing the axis, right? I've rotated, and I don't want to use I and J again, because you are referring to a different space. You've rotated, you've changed the axis. So simply a vector. Now, instead of, so are we visualizing the rotated axis? Okay, so instead of going this way, then that way, I could do this. Go this way, then that way. Same thing. The lens, B vector, A vector. The resultant is still A vector, B vector. Good. Parallelogram law. Another vector notation is to have A, B. People would write this as A, B vector. If you call that point C, you would have B, C vector. Any thoughts as to
AC.
AC vector? Good. Just different notations that people use. What makes it fun? So at the end of the day, what are we talking about? True, we are talking about vectors.
Are we just saying vector addition is transitive? As in,
Like,
Yeah, yeah. But my question is simpler than that. All this notation, all this talk with direction, magnitude, at the end of the day, what are we referring to? I'll give you a hint, geometry. Chase, or was it Chase or you? Wait, concept. What did you say?
I said a point.
Point, right? We're simply referring to a point. So I've just mentioned that at the end of the day, when we say a vector, no matter the notation, physics, math, statistics, all I'm trying to do is to refer to a point in space. Okay, that's it. This is the site that I showed last time. Purposes of visualization. Do you see a point 2, 5, 3? And that point relative to the origin is defined by a vector. Yes. So, only this time it's not just a triangle. So you take few steps this way. How many steps?
2.
2. That way. 5, and then up 3. And if you look at the notation, it is 2, 5, 3, the point. But we've used the sort of less than and greater than sign, the notation I wrote earlier. So your book uses this, the less than and greater than to represent the next. Okay. What would happen instead of drawing artist ask you this question, and whatever I'm going to show here will also hold when I talk about artists, right? We are sticking to this because convention, this is what we use in our day-to-day lives. So what would happen when I change that 2 to a negative 2?
Just goes that way.
Which way?
It goes forward in some sense.
Okay. We'll change to negative 2. Draw. Good. Direction change. So if I change that to negative 8, that would go.
To the third object over there.
Okay, let's change that to negative 8. Good. So pretty much changing direction is simply multiplying by negative 1. Good. Hold up thought. I'm going to write something in a bit. Let's just do 0. 0, 3. If I draw this, where would the vector be?
Straight up.
Straight up. Good. If I multiply by -1, the 3 by -1, that would go down. So multiplying by -1 is just reflecting from the initial point where the vector started. So you're just flipping from up to down. Good. Okay. I guess I can write it on the side here. It's not an elaborate explanation. So I'll draw two different vectors. So relative to the origin, let's say I have that vector and I multiply it by -1. So vector A multiply by -1, what happens? It goes this way. Poorly drawn, fine, you get the point. Agreed? If I multiply the vector A by, let's say, 3, what would happen?
Would get 3 times longer.
3 times longer. You're going in the same direction. The one in blue would be 3A vector. Good. So when you do scalar multiplication, it's simply increasing the magnitude of the vector. Good.